So yeah, we've looked at what it means to review one of these Python scripts, what the table definitions sort of do functionally for the SQL side, and how we manage methods associated with tables. But when it comes to designing your own, it's this process that I talked about earlier of, okay, conceptually, what are the pieces of my analysis? How do I turn them into this like flow of information that goes from one table to the next? And what assumptions do I want to bake into the analysis? What sort of structure do I want to enforce on insert? Um, versus what sort of flexibility do I want to leave my future self? Um, SQL is one way of doing things that at the beginning of the process declares, all right, these are the fields for these tables, and this is the expected structure of the data, which in more general database conversation terms is structure on read. This is different from a thing that says, oh, I'm just going to throw all of the pieces of information relevant to this unit of session data collection into a JSON file, and I will structure it when I decide to pull information from it. I think I misspoke earlier. So SQL and things like SQL are structure on write versus there are other ways to do it that is structure on read. Um, Pros and cons to each. As Spyglass is sort of tied data joint, it's what we've got. But yeah, the conceptual process of turning your custom analysis into a data joint schema, data joint pipeline is deciding what sort of structure you want to tie yourself, future self to. The process of setting up a parameters table can sometimes be as simple as this. I'm just gonna set up a blob. Yeah, Jose.
Yeah, could you explain again the difference between the structure on read and structure on write type of analysis?
Sure.
Again, I
Uh,
didn't quite
uh,
understand that.
Yeah. So SQL is a structure on write approach. I have I ran this data collection. I have some piece of conceptually linked data set, whether it has like multiple modalities. Let's say for session one, you collected EFIS and you ran a behavioral recording, some sort of recording of, nose pokes in wells, whatever. That means you expect for the course of this experiment that you are going to have the EFIS recording, the subject metadata, the timing of the nose pokes, the video, all of those like files linked to the subject. Um, if you declare a SQL database and like a data joint means of pipelining, workflow orchestration, um, you are deciding, okay, my metadata goes here, my video file goes here. And each of those relevant tables has the has the primary keys and secondary keys relevant to those files. Um, you might in the future run a recording with a new kind of data collection, a infrared video that you never collected in the past. And now you have to either decide to declare a new table. Does your existing video file table permit for this new version of recording things? Are there pieces of your function or your pre-processing pipeline that assume one kind of video over another? So that is structure on write. You force the time of data collection to be the time at which you decide the structure of that data, which makes for an easier future in which you want to like reanalyze these things. Oh, for all the video files, I have this list here, and I know they're structured like this. I can automatically do that. Um, Structure on read says I'm going to record these things, and I'm going to write this file that puts a bunch of key value pairs together, subject name, video file name, infrared video file, this name. And it might be the case that across these various folders for the recordings you have, there is not consistency across those folders. But you are going to decide the relevant pieces of consistency when you read from it and design your pipeline around that. Okay, for all of the folders that have the infrared video, I'm going to do this. That is more sort of time consuming if you don't have like a super computer, if you aren't skilled in like jobbing out things to server farms. But it allows for more future flexibility in terms of what you want your pipeline to look like.
Got it. Makes sense now. Thank you.
Yeah. Uh, so yeah, structuring on read and on write comes up a little bit in our parameter tables, where we decide a primary key, whatever param's name, and then your secondary key. You'll see cases across Spyglass where it's your secondary key is, in this case, it would be A and then integer, B integer, or cases where it's params blob, and then the blob is the dictionary of those various fields. So in the former case where we're explicitly defining the secondary keys, we that is structure on write. It forces you to have exactly this number of things, and if you're missing one or you have a third thing, it doesn't make sense, it won't run. Structure on read says, I don't know, give me whatever dictionary you got. I'll save it and hopefully it works in the future. This latter is much harder to then run a sort of restriction. If I wanted to look at all cases of my analysis where A equals 3, with secondary keys, I can run the relevant table joins that map these tables onto each other and then just say, and all cases where A equals 3. But in the case where my params is a blob, I would then have to like open up the blob, fetch it, find whether or not that key exists, and then save the primary key and run a restriction and all primary keys that have this matching criteria. That's a lot slower. So there are pros and cons to each, sort of flexibility versus capacity for querying. Uh, like I mentioned with the sort of Spyglass conceptual table types, your input data, you have to sort of decide where in existing tables that is when converting your custom pipeline or custom analysis into a pipeline in itself. Usually that's a pretty clear case of, oh, the unit of analysis that is most relevant to me is one raw file, is one row in the merge table for LFP. And you can identify that pretty cleanly by like what did I import at times when I was like sort of drafting this Python script and fleshing it out. There are sometimes cases where the thing that you are attaching to doesn't necessarily have a one-to-one correspondence with the row that you would want to insert in your selection table. So I mentioned before electrodes group as this case where there's an upstream table that lists all of the electrodes, or it's a part table associated with a more session object. If your custom analysis does that kind of grouping, I'm happy to point you to examples of grouping tables to say like, hey, maybe think about this structure as a way of putting your analysis together. I've seen some cases recently where folks are doing these like multi-session analyses. Okay, this function, is going to run on a GPU for however long, but this function considers what happened in these multiple different sessions, and it needs to have loaded all of those things at the same time. So let me write a session group table so that I can basically do the many-to-one correspondence selection process upstream of my actual selection table. Um, or sometimes the upstream table is just sort of I'll call it a pass-through table for something that exists in Spyglass. So I kind of hinted at this before, but someone asked for my help in designing a means of blinding subject data. They just didn't want to see subject ID information as they were running their analysis. So this is one way to do this, where this is a table that has one parent, one child. It inherits from subject. It passes on to a selection table for an analysis. And all it's doing is removing the visibility of the subject ID when the analysis is run by aliasing that as a secondary key and providing a UUID instead. Oh, yeah, here's the example of sort of the general structure of a grouping table. I think the harder part, in going from this general draft of a Python file that you have to a schema that works efficiently and can be used pretty readily, there's first this major decision of like, how do I conceptually separate these pieces of information? Is this one analysis table? Is this two? Um, there's the second question of what is sort of the unit of analysis in my case? Is it a group of things? Is it a sort of table within common? Is it a table downstream of some LFP processing? Um, and then the next question beyond that is which sort of subset of what I have written is a make function for an analysis table. Sort of the general structure of a make function is to first fetch from these parents. I mentioned the like joining of parent information um, into a unit so you can fetch those secondary keys, maybe fetch the parameters of your analysis. There's the fetching, the computing, and then the inserting. And there are new features of data joint that promote this and make some things happen faster. Um, but in general, I try to write these make methods such that like even in the Python sort of spacing out and paragraphing, these are separate pieces in order to make it easier to identify errors later on. Um, so you do all of the fetching first. If you have a problem, you'll see that the error occurred, in the first third of the function. You do all of the computation at once and maybe run a for loop that builds a list of planned inserts into your analysis table. And then you leave your inserts for the very end so that there are protections in place that would prevent a partial insert of like some subset of the analysis without the whole thing. But in general, if in the debugging process, I find it much easier to sort of identify where the error occurred if these pieces of run computation versus run insert are separate. So yeah, that is what takes the general notion of separating a conceptual Python draft into a schema and mapping those onto the conceptual table types from Spyglass. I'll now move on to talking about the ways that you might reference an upstream table, just because I've you know, seen some confusion from folks in the past of like, all right, how does this foreign key reference work? Why would I do one thing versus another? Um, you know, uh, uh, so a foreign key reference and like this notion of a primary versus secondary key are kind of orthogonal. Like you can have a primary key that is a foreign key reference. You can have a secondary key that is a foreign key reference. Um, so I'll, over the next couple slides, talk through the options of like, why would you primary key, foreign key, Um, why would you secondary key field these things? A single foreign key reference is sort of a pass-through table that may indicate sort of an additional processing step. I've mentioned this notion of a data params selection as like a prescriptive, follow this convention and it'll make things easier. You don't have to. You could technically design a table that just has a single um, primary foreign key reference and then attach some secondary key information to it. And in the structure of your tables, that just might represent another step in your analysis. Okay, the data has conceptually reached this point. We've added this secondary piece of information that's a result of some computation. That result may not uniquely identify this key, but we expect it to move on to the next. The presence of multiple primary foreign keys is often the sort of pairing of upstream items. I mentioned this notion of a selection table where you put these rows from two different parents together as a planned matching for something downstream. This could technically happen in the course of an analysis table if you didn't want to include this selection step. Um, Skipping the selection step just means that in the event that you run, myanalysis.populate without specifying a restriction, it's going to populate for all possible pairings of upstream information. And maybe that's desirable. Maybe you don't want this step of intentionally inserting, but yeah, we include it for filtering reasons. When you include a secondary key as a foreign key reference as a secondary key, it is often to, well, in the case of Spyglass, it's often to link some sort of structured data type. So for us, an analysis NWB file, an interval list, those are structured data types that we happen to have tables for as a means of unifying how they are declared and accessed. Um, for the case of an analysis table, you might, over the course of your make function, declare the file and then just want to have that foreign key reference so you are attaching the key to the resulting file that got computed and saved to disk, or interval list that got computed and saved in the interval list table. Um, You'll also see it happen over Spyglass that foreign key references get buried. I don't know, I think I made that up. I don't know if I've heard that before, but essentially you put all of these foreign key references as secondary keys to a table as a way of saying, I want to summarize this with just like one primary key. Um, because Spyglass is so long, because there are so many tables, it hits the upper limits by default of what SQL can handle in a primary key. It's like something like 64 kilobytes or whatever. That is the memory that is allocated for a primary key table, or sorry, for the primary key of a table. And if you go in excess of that, it will raise an error like, sorry, I can't declare this table. And rather than like keep adding and adding and adding, it's the subject name, or the subject ID, the session ID, the LFP analysis ID, the decoding analysis ID, whatever it is. All of that gets summarized, in our case, mostly into these merge IDs that just sort of represent one unit analysis from upstream, and it is not super readable, but it does help us overcome these SQL restrictions and make it significantly easier to read the downstream tables so that they're not like expanding or going beyond the width of your screen. I've put together this long distance restriction portion of the Spyglass mixin as a way of allowing folks to restrict a given table by something someplace else. Um, so by default, when you restrict a data join table, you're restricting by some primary, secondary key of the table. It's a subject table and subject ID matching this wildcard, whatever. Um, if I say LFP analysis and subject ID matching this wildcard, uh, by default, it will say this isn't a valid restriction because subject ID isn't in, whatever downstream table. But using dual greater than, less than markers using these bit shift operators in Python, you can now restrict your, downstream LFP merges by some sort of session ID, and that will sort of run through the possible parent tables saying, does it work here? Does it work here? Does it work here? Until it finds a place where it does and run the relevant join for you so that you don't have to remember to say, like, all right, LFP analysis, join LFP selection table, join, common raw, join all the way up to the place where it's actually relevant. So inconvenient, but serves its functions. Inconvenient to structure a table like this, but it serves its function. Uh, I've got about five. Okay, no, I'll just run through merge tables. Um, the process of attaching um, to downstream from a merged table can be a little tricky because it has this structure of having the UUID primary key, and it is by design sort of agnostic as to the fields contained in its parents. To design an analysis downstream of a merge table would require a lot of very careful conditional, like, okay, if the source of this data has this field, then do that, and force you to set up these conditionals for the various pipelines it inherits from. Um, the I've put together a series of merge table functions that by design do that, like conditional if then sorting for you so that you can, for example, get all of the, primary and secondary fields of the table that the merge table inherits from. Um, so while I won't go into detail on them now, the I've done my best with the documentation to say, like, hey, if you want to inherit from a merge table and run analyses over multiple pipelines, here's how to do so. Um, yeah. Uh, does that make sense? Does that sort of feel relevant to the kinds of things that you will maybe want to turn into data join tables? I hope so. Okay, with the next 5 or so minutes, I'll just cover some of the errors that you're likely to encounter getting started with data join, getting started with Spyglass, and their likely causes. Yeah, go ahead, Gabby.
Yeah, sorry, before you get into that, I had a
Mhm.
question about how to handle like data frames that you want to save out from analysis pipelines, and if like maybe saving out a data frame is not the best practice in like a blob format in a table. But I guess with the functions that do call like fetch data frame, where is that data frame being stored? Is that from like an analysis NWV file? How does I just don't really understand how that works.
Yeah, I think so. I think tables allow for different ways of storing data frames. So if like you're curious about a specific table, does it have a fetch one data frame method? You can go like look at the table definitions in the Python file. For the most part, I think our default for fetch one data frame, correct me if I'm wrong, Sam, is to look at the stored analysis NWB file and fetch the relevant object pertaining to that table.
Yeah,
Does
so like,
yeah.
oh, sorry. When you're like making a custom pipeline, most of the time, pretty much all computed tables will have a foreign key reference to analysis NWB file, which is a Spyglass table that we use to kind of organize and has useful methods for storing data on disk. So you do an analysis, you have this big data frames are common. You don't want to put it in an SQL table because that's going to slow things down for everyone. So our kind of protocol is you link to analysis NWB file, like have a foreign key reference there. And then in your make function, you would, you can look at like LFPB1. There's a good number of tables with examples. There's a method to create an analysis NWB file on disk, and then add an NWB object to that. So that can be any NWB object, like a time series, stuff like that, or a pandas data frame. If you pass that function a pandas data frame, it'll put it in the file in a compatible way. And so that is definitely the recommended way to kind of store these results, so that you don't bog down tables. And then functions like fetch NWB can be used to go and retrieve that data when you want to do something afterwards.
Okay, cool. Yeah, that's very helpful to know the general framework of how to set that.
Yeah, so there's a few methods to that table. LFPB1's probably a reasonable like example of essentially you create a file on disk, you add your objects, and then you insert that as a new entry into analysis NWB file so that the database knows how to go and access that.
Cool. Yeah.